Hi guys, let's go ahead and start chapter 11.4, composite figures and area notes. So this is the last section of unit 4. So let's go ahead and start with example 1, where it says identify segments and angles in regular polygons. So it says the square FGHJ, which is right here, is inscribed in a circle K, in point K right here. Identify the center, a radius, an apothem, and a central angle of the polygon. Then find the measure of a central angle. So the center point, the center is point K, because K is right in the center. The radius is going to be half of that whole diagram right there. So it's going to be K to H, or K to G. So notice that this K all the way to the H touches the outside of the circle. So does K to G. So it's going to be KH or KG. The apothem is going to be KL, because it's the inside radius of that inside figure. So KL. And then the central angle is going to be angle GKH. GKH, which is this angle, because it's in the center of that entire object. So angle GKH. Okay, now to find the measure of the central angle. Since a square is a regular polygon with 4 sides, the measure of each central angle is going to be 360 divided by 4. Because remember, for central angle, the formula is 360 divided by n. Well, a square has 4 sides, and n stands for sides. So this is 360 divided by 4, which is 90 degrees. Okay. Let's go ahead and look at example 2. Okay, so it says, Kong created the stained glass window shown. The window is a regular octagon with a side length of 15 inches and an apothem of 18.1 inches. What is the area covered by the window? So first, we're going to divide the polygon into congruent isosceles triangles. This is what you see outlined in yellow. Since the polygon has 8 sides, the polygon can be divided into 8 congruent isosceles triangles, each with a base of 15 and a height of 18.1. Now we need to find the area of one of the triangles. Well, remember, the area of a triangle is 1/2 base times height. Well, our base is going to be 15, and our height is going to be 18.1. So area is equal to 1/2 times 15 times 18.1. Well, this comes out to 135.75 inches squared. Now we need to multiply the area of one triangle by the total number of triangles. Since there are 8 triangles, we're going to multiply this number by 8. When we multiply it by 8, we get 1,086 square inches. So this is the area of the entire window. Area of window. Okay. Now let's look at example 3. But before we do that, we're going to check out this key concept. So the area A of a regular n-gon, so n just means number of sides, with side length S is 1/2 the product of the apothem A and the perimeter P. So this just gives you an example what it's talking about. So we're going to use that formula to find the area of each regular polygon, and we're going to round to the nearest tenth. The first one is a regular hexagon. So first we need to find the measure of the central angle. So central angle. Remember that formula is 360 divided by n. Well, since this is a hexagon, 360 divided by 6 is what we're looking for because n is the number of sides, hexagon means 6 sides. So this is going to be 60. Now we're going to find the apothem. The apothem, BD, is the height of the isosceles triangle ABC. It bisects angle ABC, so the measure of angle DBC is 30. So DBC is 30. Because remember, an isosceles triangle has an angle of 60 right here. So if it's half of it, because it bisects, then it's 30. It also bisects AC. So DC is 1.5. So DC, which this part, is 1.5 because it's half of 3. The triangle BDC is going to be 30 degrees minus 60 minus 90 degrees. Triangle with a shorter leg then measures 1.5 meters. So that means that BD is going to be 1.5 square roots of 3 meters. So triangle BDC, which is that little triangle, triangle BDC is going to be 30 minus 60 minus 90. Sorry, it's not minus, those are 30 degrees, negative 60 degrees, and negative 90 degrees, with a shorter leg that measures 1.5. So that means that BD is equal to 1.5 square roots of 3, which is also the apothem. So now, using the formula, we have A is equal to 1/2 little a by P. Okay? This is going to be the area of a regular polygon. So we have 1/2 times the apothem, which is 1.5 square roots of 3, times P, which is going to be all of the sides together. So since this is a hexagon, we're going to have 6 times 3, which is 18. So this times 18. So when we multiply these all together, this is about 23.4 meters squared. Okay, let's look at part B. Okay. A regular pentagon has 5 congruent central angles. So in order to find the measure of angle QPR, we're going to take 360 divided by 5, which is equal to 72. Okay, so QPR, so this whole thing is 72. The apothem, PS, is the height of the isosceles triangle RPQ. It bisects angle RPQ, so that means the measure of angle RPS is 36, because it's dividing it in half. So the measure of angle RPS is equal to the measure of angle QPR divided by 2, which is 72 divided by 2, which is 36. Use using ratios to find the side length and apothem of the polygon. This is what we have. sine of 36 degrees is equal to SR over 10. This is the same as saying 10 sine 36 is equal to SR. Okay? And then we have cosine of 36 is equal to PS over 10, which is the same as saying 10 cosine 36 equals PS. QR is equal to 2SR, or 2 times 10 sine of 36 degrees. So the pentagon's perimeter is going to be 5 times that, 5 times this right here, so this whole thing times 5, which is 10 times 10 sine 36. The length of the pothom PS is 10 cosine 36, which we already have up here. Okay. Now using the formula, we have area is equal to 1/2 the apothem P. So we have area is equal to 1/2 10 cosine 36 times 10 sine 36. If we plug all this into our calculator, we get 237.8 inches squared. And this is the area of the entire pentagon. Okay. Let's continue to example 4. Okay, example 4 says, when viewed from above, the putting green at a miniature golf course is composed of a semicircle, trapezoid, and triangle. Which of the following best represents the area of carpet needed to cover the green? So the area to be carpeted can be separated into a trapezoid with a height of 7 feet and a base of 2 feet and 4 feet, a triangle with a base of 3.25 feet and a height of 7.75 feet, hypotenuse of 5.7 feet, and a semicircle with a diameter of 2 feet. We need to find the area of each of them separately and add them together. So first, we need to remember what the area of each of these are. So the area of green is going to be equal to the area of a trapezoid plus the area of a triangle plus the area of a semicircle. So if we have each of these formulas, we have the trapezoid formula, which is 1/2 times height base 1 plus base 2, plus area of a triangle, 1/2 base height, plus area of a semicircle, 1/2 pi r squared. So if we plug in all the data we have on this, we have 1 height times 7 times 2 plus 4 plus 1/2 times 3.25 times 7.75 plus 1/2 pi 1 squared. So if we plug that into the calculator, we get 21 plus 12.59 plus 1.57, which is equal to 35.16 feet squared. So they'll need about 35 square feet. They will need about 35 square feet of carpet. So that means the answer is C. Okay. We have one more example, and that's example 5. Find the area of the figure and round to the nearest tenth if necessary. To find the area of the figure, we need to subtract the area of the triangle from the area of the rectangle. We need to use the Pythagorean theorem. The height h of the triangle is, so we're saying that this right here is going to be the height h. Okay? So using the Pythagorean theorem, we have 4 squared. So let me start writing this down. Pythagorean theorem. We have the square root of 4 squared minus 3 squared, which is the square root of 16 minus 9, which is equal to the square root of 7. So that means the area of the figure, so area of figure is equal to the area of a rectangle minus area of a triangle. So we have base times height minus 1/2 base times height. Well, base times height for the whole rectangle is 5 times 6. Oops. 5 times 6 minus 1/2. The base of the triangle is 6. And the height is what we found, which is the square root of 7. So if we simplify this, we get 30 minus 7.9, which is about 22.1 meters squared. So this is the area of that blue space that we needed to find. And this concludes the notes for 11.4.